What if the most mysterious objects in the universe were also the ones most misunderstood? Black holes are often presented as simple cosmic traps, places where everything disappears forever. But the truth hiding behind that darkness is far stranger and far more beautiful than anything most people ever learned in school. They bend reality in ways that seem almost impossible, turning gravity into a quiet sculptor of time and light. Tonight, you're wrapped in a calm that feels almost weightless, the kind of stillness that makes distant galaxies easier to imagine. The room around you is soft, the night unmoving, and your own breathing falls into a slow, steady rhythm. In this gentle quiet, the universe feels closer, as if the space between here and the stars has thinned just enough for your mind to drift freely. Black holes hold a special kind of truth, one rarely explored in classrooms. They stretch the rules of physics, twist the flow of time, encode information in ways that seem impossible, and reveal hidden layers of the universe that textbooks barely touch. The deeper you look into them, the more you realize they're not terrifying voids. They're doorways into a richer understanding of reality that school never truly revealed. And if wandering through these cosmic mysteries makes your night a little quieter, or your thoughts a little lighter, you're warmly invited to leave a like and subscribe to the channel. It's a gentle way of helping this peaceful space reach others who enjoy drifting through the unknown. And I'm grateful for every moment you choose to spend here. So let's follow this thread together. Somewhere beyond ordinary explanations lies a realm where gravity folds space, where time stretches thin, and where the universe hides the things it didn't teach us, waiting patiently for those curious enough to look deeper. There's something almost paradoxical about the fact that the most feared objects in the universe begin with nothing more dramatic than gravity doing what it always does. Massive stars spend millions of years burning fiercely, holding their own weight at bay. But when the last elements in their cores fuse together, the delicate balance that kept them alive collapses. In that single moment, gravity wins completely, pulling everything inward with unimaginable force. Astrophysicists describe this collapse with exquisite precision. When a star several times the mass of our Sun runs out of fuel, its iron core can no longer support the outward pressure from nuclear fusion. Gravity crushes the core in a fraction of a second, causing the outer layers to rebound outward in a violent supernova explosion. What remains in the center is a compact object so dense that normal matter cannot resist its weight. Trying to picture this density is almost impossible. Imagine compressing a mountain into a teaspoon, or squeezing the mass of a star into a sphere smaller than a city. The result is a gravitational well so deep, so absolute, that even light cannot climb out. The star doesn't disappear, it becomes something new, something the universe treats differently from everything else. And that transformation feels strangely poetic. A star spends its life shining, radiating light into the darkness, only to end as an object that allows no light to escape. It is a journey from brilliance to silence, from generosity to secrecy. There's something in that arc that mirrors the quiet, inward-turning moments of a human life, when energy outward becomes reflection inward. The boundary surrounding this transformed object is called the event horizon, and it behaves less like a surface and more like a point of no return. Anything that crosses it, matter, light, information, cannot come back. To an outside observer, time appears to slow dramatically near this boundary. Particles falling inward stretch, fade, and freeze in place, though the reality from the inside is very different. General relativity predicts these distortions with remarkable accuracy. Near a black hole, space-time curves so sharply that paths which would normally carry objects outward from gravity now bend inward inexorably. Light rays follow these curved paths too. Even if a photon tries to escape, the curvature redirects it back toward the center. This isn't suction. It's geometry warping into a shape you cannot escape once you cross a certain threshold. The idea of space-time bending like fabric is helpful, but incomplete. A more accurate metaphor is imagining a landscape where every direction slopes downward. Even if you try to move sideways, the ground tilts beneath you, guiding you inward. Nothing pushes you. You simply follow the terrain. A black hole is the steepest valley the universe allows, a drop so deep that climbing out becomes impossible. There's a philosophical quietness in realizing that black holes don't pull. They merely reshape the map. They rewrite the meaning of direction itself. And in that rewriting, they remind us that the universe is not built from objects alone. It is built from relationships, curves, and flows invisible to our senses. Their existence hints at a cosmos far stranger than the one we perceive. One of the most surprising truths hidden from most school lessons is that black holes are not empty. The name suggests a void, a hollow pit, a region with nothing inside. In reality, they're made of the collapsed remnants of massive stars, compressed into an exotic state of matter we can barely describe. Beneath the event horizon, physics becomes so extreme that our equations stutter, hesitate, and ultimately fail. Einstein's relativity predicts a singularity, a point of infinite density and zero volume, but quantum physics forbids infinities. The conflict between these two pillars of modern science is one of the reasons black holes fascinate researchers. They are natural laboratories where gravity and quantum mechanics meet, where we can test ideas that push beyond the limits of known physics. Trying to imagine the singularity is like trying to imagine the color of silence. It doesn't fit into our conceptual language. Instead of thinking of it as a point, some theorists believe it may be a region of extremely compressed quantum states, a place where space and time dissolve into something more fundamental. That hidden core is not visible from the outside. All we can observe is the event horizon, the shadow of deeper mysteries. The event horizon acts as a one-way mirror. It reveals nothing about the interior, yet dictates everything about how the black hole interacts with the universe. Light orbiting near it can form rings, looping endlessly before choosing a direction. Time slows dramatically as gravity intensifies. Even the flow of cause and effect warps. To an outside observer, a falling object never truly crosses, it just appears to fade. Imagining that boundary evokes a feeling of standing at the edge of an ocean at night. You sense depth, movement, and power, yet everything beyond a certain distance is swallowed by darkness. The horizon doesn't mark an end to the sea. It marks an end to what your eyes can see. The black hole's edge functions the same way, a limit not of existence, but of perception. This separation between what exists and what can be observed carries profound implications. Information falling into a black hole should, according to classical physics, be lost forever. But quantum mechanics insists information is never destroyed. This disagreement between laws of nature sparked one of the most famous scientific debates of the last century, involving Stephen Hawking, Leonard Susskind, and many others. The tension led to the realization that black holes might encode information on their surfaces, on the event horizon itself, rather than storing it inside. This idea paved the way for the holographic principle, which suggests the universe might fundamentally store information in 2 dimensions, projecting the 3-dimensional world we experience. It's a concept so strange that it feels like stepping into science fiction, yet it's grounded in rigorous mathematics. Imagining the event horizon as a cosmic hard drive changes the way we see these objects. They are not bottomless pits swallowing knowledge. They are archives preserving it in encoded form. The surface area of the horizon, not the volume within, determines how much information the black hole can store. This flips our intuition completely, and reveals just how limited our everyday understanding of space truly is. Reflecting on that idea creates a softness in the mind, as if the universe were whispering that reality is far richer than our senses imply. Black holes, instead of being cosmic destroyers, might be keepers of memory, preserving the imprints of everything that falls in. The cosmos begins to resemble something layered, intentional, not in a mystical sense, but in a mathematical one. Another hidden truth rarely taught in school is that time behaves dramatically differently near a black hole. For someone falling in, moments continue normally. But for an outside observer, the clock of the falling traveler slows, stretching each second into longer and longer intervals. A person spiraling inward could live a lifetime in what appears to be just an instant from their perspective. This time dilation arises directly from Einstein's relativity. Gravity is not a force pulling downward, it is curvature guiding motion. The stronger the curvature, the slower time flows. Near a black hole, time slows to such extremes that the interior may exist in an entirely different temporal state. It is as if two worlds coexist at different speeds, separated only by the horizon. Picturing that separation calls to mind the image of two rivers flowing side by side, one moving swiftly, one nearly still. Both rivers are made of the same water, yet their currents differ. In the same way, time flows at different rates depending on gravity's pull. A black hole is simply the most dramatic expression of that universal truth. This divergence in time leads to another wonder. From an external viewpoint, anything falling in appears suspended forever, frozen just above the horizon. But from the inside, it passes through effortlessly. Reality doesn't disagree. It simply reveals that perspective shapes everything. What you see depends on where you stand in space-time. That realization invites a philosophical tenderness. It reminds us that truth in the universe often comes in layers. There is no single perspective that captures everything. Black holes embody this duality. Unreachable interiors paired with visible shadows, frozen edges paired with flowing cores. They are contradictions only because we try to see them through one lens at a time. As you drift deeper into these ideas, the familiar fear around black holes fades. What replaces it is curiosity, gentle, steady, and open. These objects aren't monsters hiding in space. They are gateways to the limits of physics, invitations to explore concepts that stretch beyond intuition. And as strange as they are, they fit perfectly into the universe's quiet logic. Somewhere inside all these ideas lies a subtle hint at an even bigger mystery, one that researchers have only begun to touch. It glimmers softly beneath everything we've explored so far, waiting for the right moment to emerge. And as we continue into the next layer of the cosmic story, that mystery begins to come into focus, pulling us deeper into the gentle gravity of the unknown. Most people grow up with the image of a black hole as a perfectly still sphere, quietly swallowing everything around it. But real black holes almost never sit motionless. They spin, and their rotation changes everything. A rotating black hole behaves more like a cosmic whirlpool, dragging space-time along with it as it turns. This effect, known as frame dragging, twists the very fabric of reality into a spiraling flow that no classroom diagram ever captures. Einstein's equations predict this dragging with remarkable clarity. When a massive object rotates, it pulls space-time into a swirl around it. Near Earth, the effect is tiny, so tiny that only extremely sensitive experiments like Gravity Probe B could detect it. But near a spinning black hole, the effect becomes overwhelming. Space itself is forced to rotate, becoming part of the black hole's spin. Trying to visualize this cosmic whirlpool feels like imagining a river whose current becomes so strong that even the shoreline starts to drift. The water doesn't just move within the riverbed twists with the water. A rotating black hole bends everything around it into a spiraling dance, where motion and space are inseparable. Reflecting on this motion evokes a quiet wonder. The universe isn't made of rigid, unmoving pieces. It flows, bends, stretches, and turns. A black hole's spin is a reminder that even the most extreme objects in existence follow the same fundamental rhythm of movement that shapes galaxies, stars, and even the atoms inside your body. Few teachers ever mention that rotation dramatically changes a black hole's structure. Instead of a single boundary, a spinning black hole has two: the event horizon and the ergosphere. The ergosphere is a region outside the horizon where space-time is dragged so violently that nothing can remain still. In this region, standing motionless is impossible. Everything is forced into motion, even if it doesn't want to move. Scientists describe the ergosphere with elegant mathematics. It forms a sort of stretched, oblate shell around the black hole, bulging outward at the equator where rotation is strongest. Inside it, particles and light lose their ability to resist the flow of space-time. They're not falling in, they're being carried along by the geometry itself. For something to remain stationary, there would require faster-than-light motion, which nature doesn't allow. Picturing the ergosphere feels like imagining a giant, invisible tide pulling everything around it. Objects don't sink. They swirl, caught in a gravitational current that even light cannot outrun. It's a region of surrender, where motion becomes a requirement rather than a choice. There's a strange comfort in the idea that some places in the universe simply won't let you be still. The cosmos is full of regions where movement is inevitable, where drifting is not a flaw, but a natural consequence of being immersed in something larger. The ergosphere is an extreme example, but the feeling is universal. Some forces are too vast to resist. One of the most astonishing discoveries hidden from most school lessons is that the ergosphere allows energy to be extracted from a black hole. This process, first theorized by Roger Penrose, shows that spinning black holes can give up part of their rotational energy. If a particle enters the ergosphere and splits, one fragment can fall in, while the other escapes with more energy than it began with. Physicists have tested versions of this process in simulations, and the results reveal staggering possibilities. In theory, black hole rotation could power enormous jets of energy, streams of particles accelerated to near light speed and flung out into space. These jets, observed by telescopes like NASA's Chandra X-ray Observatory, often extend for thousands of light years. Thinking of a black hole releasing energy feels like watching a storm illuminated by a sudden flash of lightning. What appears dark and consuming turns out to be capable of immense radiance. The black hole, usually portrayed as a cosmic devourer, becomes a generator, one of the most powerful energy engines in the universe. This dual nature encourages a deeper reflection. Nothing in the universe is only one thing. Dark things can produce light. Destructive things can create order. Even the most intimidating objects can offer pathways to understanding and growth. Black holes embody this paradox elegantly and silently. Magnetic fields amplify this paradox even further. Near a spinning black hole, magnetic field lines twist around the swirling plasma, winding tighter and tighter until they snap and reconnect. This process accelerates charged particles at incredible speeds, launching them into space as brilliant jets that pierce the darkness like cosmic lighthouses. Astrophysicists observe these jets across the electromagnetic spectrum. Radio telescopes map their vast shapes. X-ray telescopes capture their intense heat. Even infrared observatories detect their glow. These jets slice through space for unimaginable distances, carrying energy from a region smaller than our solar system across expanses bigger than entire galaxies. Visualizing these jets is like imagining a firefly glowing at the bottom of an ocean, its faint light somehow piercing through miles of water. Something so small creates a beam that stretches impossibly far. It's a reminder that scale in the universe is as irrelevant to power as size is to significance. The existence of these jets reveals that black holes are not silent. They do not simply sit in the dark. They shape galaxies, regulate star formation, and heat the gas in galaxy clusters. They play roles more creative than destructive. Without them, the universe would look very different, less structured, less dynamic, less alive. Pondering that influence brings a sense of humility. We often imagine black holes as isolated monsters lurking in distant corners, but in reality, they are central players in cosmic evolution. They sculpt galaxies the way rivers sculpt valleys, by guiding matter with slow, patient force over billions of years. Another misconception rarely challenged in school is the idea that black holes suck everything in. In truth, an object orbiting a black hole behaves much like it would orbit any massive body. If the Sun were replaced with a black hole of equal mass, Earth would continue orbiting normally. The days would stay the same length, the year unchanged. What changes is not the orbit, but the fate of anything that falls too close. Understanding this reality dissolves the fear that black holes roam the universe as cosmic vacuum cleaners. They follow the same gravitational rules as stars. Only at their very edges do things become strange. The danger lies in proximity, not intention. That knowledge leads to a quiet insight. The universe is not hunting us. It isn't hostile or predatory. It simply follows its own laws, indifferent but consistent. Black holes are extreme only because they obey those laws to their fullest expression. The more we uncover, the clearer it becomes that black holes reveal the flexibility of space-time. They show that time can slow, stretch, or nearly stop. They show that space can twist, flatten, or fold. They show that energy can be extracted from darkness itself. And all of this emerges from pure geometry. Nothing mystical, nothing supernatural, just the shape of reality expressed under extreme conditions. Sitting with these truths evokes a gentle awe. It's strange to think that such violent phenomena can arise from equations, symmetries, and curves. Yet that's what makes them so compelling. Their mystery is not born of chaos, but of order so deep that it feels like poetry written in gravity. And somewhere within this dance of spin, light, and curvature lies a deeper enigma, one that scientists are still trying to understand. Something about spinning black holes hints at a truth bigger than rotation alone. Something older, something waiting just beneath the shadows of their swirling horizons, ready to reveal itself as we drift further into the cosmic story. There is a strange duality at the heart of black holes, a kind of cosmic split between what is seen and what is experienced. To an outside observer, anything falling toward a black hole appears to slow down, dim, and freeze just above the event horizon. But from the perspective of the falling object, there is no pause, no hesitation, no moment of suspension. The journey continues smoothly, as if nothing unusual has happened at all. Physicists have long marveled at this contradiction. According to general relativity, time runs differently depending on gravity. Near a black hole, the curvature becomes so intense that clocks closer to the horizon tick slower compared to clocks farther away. This isn't an illusion. It's woven into the geometry of space-time. Time itself stretches, thins, and elongates. Trying to visualize this temporal distortion invites comparisons to a river widening as it approaches a waterfall. From far away, the water seems calm and steady, flowing effortlessly toward the edge. But up close, the current accelerates, the surface tightens, and the world changes. Both perspectives describe the same river, yet they feel radically different depending on where you stand. Reflecting on this difference highlights a deeper truth. The universe doesn't offer a single viewpoint. It accommodates many. Reality shifts depending on the observer's position, motion, and gravity. This flexibility isn't a flaw, it is part of the elegance of physics. Black holes simply showcase that flexibility at its most dramatic. One concept missing from most school lessons is the idea of proper time, the time experienced by an individual following their own path through space-time. Proper time explains why falling into a black hole feels ordinary to the traveler. They cross the horizon in a finite amount of personal time, unchanged in their own frame, while the outside world sees something entirely different. Inside this framework, the event horizon loses much of its mystery. It isn't a fiery boundary, nor a wall, nor an instantaneous destruction zone. It's simply a region where all possible paths forward lead deeper inside. The geometry funnels everything inward gently but inexorably. Nothing violent happens at the horizon itself. The real extremes lie far beyond. Imagining this crossing is surprisingly serene. A traveler drifting inward would see the universe behind them speed up, the stars aging rapidly, the expansion of space accelerating, entire cosmic eras passing in moments. It would feel like watching time unspool at fast forward while they move forward in normal pace. The experience would be beautiful and terrifying in equal measure. This strange flow of time leads to profound questions about fate and causality. If you fall into a black hole, the rest of the universe races into the far future before you reach the interior. It's as if you become untethered from the normal flow of history, entering a region where time behaves differently from the entire cosmos outside. Philosophers often point out how this challenges our sense of continuity. We live our lives assuming time is universal, the same for everyone, everywhere. Yet black holes reveal how deeply personal time really is. Each observer carries their own clock, their own rhythm, their own unfolding of moments. No two paths match perfectly. As the traveler continues deeper, the tidal forces begin to grow. These forces arise because gravity changes from one location to another. In smaller black holes, these differences become extreme, stretching the body head to toe in a process known as spaghettification. But in large, supermassive black holes, the curvature changes so gradually that a person could pass the horizon without feeling anything dramatic at all. The subtlety of this entry surprises most people. Popular culture paints black holes as instant death traps, but reality is more nuanced. The true violence lies farther inside, near the central region where space-time curves so intensely that classical physics becomes useless. The horizon is simply a gateway, not a guillotine. Understanding this helps break another misconception. Black holes don't immediately destroy everything they touch. Instead, they guide matter along paths dictated by the structure of space-time. What we interpret as being crushed is really matter following the deepest slope in the universe, unable to resist the shape of the geometry. Imagining that slope is like visualizing a vast, invisible funnel carved into the fabric of existence. Nothing pulls you in. Instead, every path naturally leads downward. The deeper you go, the steeper the descent, until all possible directions point inward. It is the ultimate one-way landscape. This yields a curious emotional response. There's a quiet, melancholy beauty in realizing that even the most violent phenomena arise from order. Black holes are not chaotic monsters. They are predictable expressions of geometry. Their behavior follows rules so precise that entire civilizations could navigate by them if they understood their structure well enough. Such precision makes black holes powerful teachers. They reveal the nature of gravity at extremes, the fragility of time, and the importance of perspective. They show that horizons can exist not just in space, but in understanding, boundaries where familiar interpretations fail and new frameworks must emerge. As the traveler approaches the region where physics breaks down, quantum theories begin to compete with relativity. The equations suggest space-time may become granular, energetic, turbulent. The smooth continuum described by Einstein gives way to something more pixelated, more restless. more alive with uncertainty. These quantum fluctuations form a storm no one can fully describe. Space may pulse with energy, time may jitter or fragment. The familiar concepts of distance, direction, and causality may evaporate. This interior realm is so foreign to human intuition that even metaphors struggle to capture it. Thinking about such a place is like imagining an ocean made of shifting reflections, patterns that form and dissolve faster than you can interpret them. The deeper you look, the more the boundaries blur, until all you see are hints of structure dancing in a world without anchors. Scientists suspect this chaotic region hides profound truths. It may hold clues to quantum gravity, the unification of forces, the nature of space-time, and the identity of the singularity. It may reveal why information cannot be destroyed and how black holes eventually evaporate. It may even connect to the earliest moments of the universe. Pondering these possibilities brings a sense of reverence. Black holes are not just cosmic oddities, they are gateways to knowledge so deep that even now, decades after Hawking's first breakthroughs, we stand at the edge of understanding. The universe isn't hiding the truth, it's inviting us to look closer. As the traveler approaches the innermost regions, the difference between interior and exterior dissolves. There is no turning back, no alternative path, no familiar horizon. All that remains is the descent into a place where the universe folds into itself, where the meaning of inside loses coherence, and where new physics waits in the quiet darkness. And just before the traveler reaches that final region, before space-time becomes unrecognizable, there is a moment of profound stillness, a pause, a breath. A hint that the greatest mystery of all lies just past the limits of our theories, waiting patiently for us to uncover its truth. At the center of almost every large galaxy lies a supermassive black hole, a gravitational anchor millions, sometimes billions, of times more massive than the Sun. It may seem counterintuitive that something defined by darkness could shape an entire system of stars, but supermassive black holes are among the most influential structures in cosmic evolution. Their presence is subtle yet decisive, guiding the behavior of galaxies without ever needing to reveal themselves directly. Astronomers have spent decades studying how these giants form. The leading theories suggest they grow through a combination of rapid accretion and mergers with smaller black holes. Early in the universe, matter was denser, so collapsing gas clouds could feed them quickly. Over billions of years, each collision, each swallowed star, each tidal disruption added to their mass, turning them into the engines we observe today. Trying to picture such growth evokes the image of a seed becoming a vast ancient tree. Each fallen leaf, each absorbed drop of water contributes to its expansion. Nothing appears dramatic in the moment, but the accumulation of small events builds something enormous. A supermassive black hole grows the same way, quietly, steadily, inevitably. That comparison reveals something profound about scale. In human terms, a single lifetime feels long. But to galaxies, time passes like slow breaths. Their central black holes shape their structure across epochs so vast that human intuition simply dissolves. Watching a galaxy evolve would require patience beyond the limits of biological minds. Evidence from observatories like NASA's Chandra and ESA's XMM Newton shows that black holes regulate star formation by heating or expelling gas. When material spirals inward, the energy released can be tremendous, powerful enough to push matter away from the galactic core. This feedback stabilizes the galaxy, preventing runaway star formation that would otherwise exhaust the available gas. The process can be described with elegant clarity. Accreting matter forms a disk around the black hole, heating to millions of degrees as friction and compression intensify. This hot plasma emits radiation, and produces powerful winds that sweep outward, influencing regions thousands of light years away. The black hole doesn't choose to shape the galaxy, it simply does, by following the physics of momentum and energy. Visualizing this influence feels like imagining a small flame warm enough to shape the frost patterns on a window. The flame isn't touching the glass, yet its heat determines the delicate branching of ice. The black hole, though tiny compared to the galaxy, guides the flow of matter with similar subtlety and power. It's humbling to realize that without these central giants, galaxies might collapse into chaotic structures. They provide a kind of gravitational choreography, ensuring that stars orbit harmoniously instead of spiraling unpredictably. Their stabilizing effect is one of the universe's quiet marvels. This understanding challenges the simplistic view taught in many classrooms, that black holes are purely destructive. In reality, they are gardeners of the cosmos, regulating growth, maintaining balance, and shaping the environments where stars and planets can form. Their darkness is not emptiness, it is structure. Astronomers often explore this idea through simulations. These digital universes reveal that galaxies with supermassive black holes evolve more smoothly, with cleaner spiral arms, more stable rotation curves, and more predictable star distributions. Without them, galaxies warp, twist, or fragment. Their presence is like gravity's signature carved into the architecture of everything. Thinking about this guardianship brings a sense of cosmic reverence. It's astonishing that something invisible, something hidden behind a boundary we cannot cross, exerts influence on scales larger than imagination itself. It reminds us that power in the universe often resides in the quietest places, those without light, without spectacle, but full of gravity. Observations of active galactic nuclei show even more dramatic examples of this influence. When supermassive black holes accrete large amounts of matter, they shine brighter than entire galaxies. Their jets can pierce intergalactic space, heating gas between clusters, shaping the cosmic web. These outbursts happen over millions of years, yet their traces remain carved into the universe for eons. Imagining a galaxy lit by an active nucleus feels like watching a lantern glow inside a vast cathedral. The illumination fills the expanse, bouncing off invisible walls, revealing structures once hidden in shadow. Something so small compared to the surrounding space becomes capable of shaping everything. Another rarely taught truth is that stars near the center of galaxies move at astonishing speeds. Measurements from observatories like Keck and VLT show stars slingshotting around the central black hole at thousands of kilometers per second. These orbits provide direct evidence of the black hole's mass. Even though we cannot see it directly, the motion of those stars feels almost musical. Each orbit is like a note in an ancient symphony, repeating endlessly, shaped by gravity's rhythm. Their dance reveals secrets without needing words. They show us that the universe communicates through motion as much as through light. In the Milky Way, the star known as S2 has an orbit so elongated and swift that it completes a loop every 16 years. When it reaches its closest point to Sagittarius A, our central black hole, it accelerates to an astonishing fraction of the speed of light. Observing this motion confirmed Einstein's predictions about space-time curvature with striking precision. Reflecting on S2's journey evokes a sense of awe. A single star, surrounded by darkness, becomes a messenger of fundamental truths. Its path tells us how gravity behaves, how space-time bends, and how the unseen can still be measured. It is a reminder that knowledge doesn't always require visibility. Sometimes motion alone carries the answers. Another overlooked detail is that black holes influence not just their own galaxies, but also neighboring ones. When galaxies collide, their central black holes spiral toward each other, eventually merging in a burst of gravitational waves. These cosmic ripples first detected by LIGO in 2015, travel across the universe as faint tremors, marking the moment two massive objects became one. Imagining these invisible waves spreading outward feels like hearing a distant bell through layers of fog. You can't see the bell, but the vibration reaches you, telling you something profound has occurred. These waves are signatures of cosmic transformation, carrying the memory of collisions across billions of light years. As galaxies continue to evolve, their black holes grow, merge, and reshape the universe's large-scale structure. Their influence extends far beyond the immediate vicinity of their horizons. They help define the cosmos not just through their gravity, but through their energy, motion, and interaction with the environments around them. All of these truths overturn the idea that black holes are isolated. They are woven into the universe's fabric, shaping stars, galaxies, and even the cosmic web. Their presence is a thread running through everything, subtle but essential. And somewhere within that thread lies a clue, something hinted at by their behavior, their power, and their silence. It is a truth deeper than gravity alone, a truth waiting to reveal itself as we drift further into the heart of their darkness. One of the most astonishing truths about black holes is that they challenge the very idea of information itself. School lessons often teach that whatever falls into a black hole is gone forever, erased from the universe. But physics refuses to accept erasure. Every particle carries details: mass, charge, quantum state, and quantum theory insists these details cannot truly be destroyed. And so, black holes become battlegrounds between the deepest principles of nature. For decades, Stephen Hawking believed that black holes evaporate through a process now called Hawking radiation. According to his calculations, particle-antiparticle pairs forming near the horizon result in a slow leak of energy. Over unimaginable timescales, a black hole can shrink, fade, and eventually vanish. But this leads to a troubling paradox. If the black hole disappears, where does the information go? Trying to grasp this paradox feels like imagining a library slowly dissolving into mist. The books vanish page by page, leaving nothing behind. But quantum mechanics tells us the story written in those books must persist somewhere, encoded, transformed, preserved. It cannot simply slip into non-existence. And so scientists realized the universe was hinting at something far deeper than anyone expected. Reflecting on this conflict reveals how fragile our assumptions about reality truly are. We imagine the universe as logical and consistent, but black holes show us the edge where logic bends, where familiar rules blur, and where new frameworks must emerge. They are not contradictions, they are invitations to expand our understanding. Some researchers propose that information might not disappear, but instead be scrambled and encoded on the event horizon itself. This idea led to the holographic principle, the notion that everything happening inside a region of space could be represented by information stored on its boundary. It suggests the universe works less like a volume and more like a surface. Imagining reality as holographic evokes a haunting image. You can picture the universe as a vast cosmic stage, where depth and dimension arise from patterns etched on the edges. It's not that the three-dimensional world is fake, it's that its foundation is stranger, thinner, more delicate than anything we were taught. The brilliance of the holographic principle lies in its simplicity. Instead of assuming information vanishes inside a black hole, the universe stores it where it can be preserved, on the horizon, encoded in subtle fluctuations, waiting to be released again through Hawking radiation or gravitational waves. The black hole becomes less a tomb and more a vault, and that vault leads to a philosophical shift. Everything falling into a black hole leaves a trace. Nothing is wasted. Nothing is forgotten. The universe remembers every interaction, every particle, every ripple in space-time. Black holes don't hide information, they transform it, preserving the essence even as the form dissolves. Entanglement plays a crucial role in this transformation. Quantum entanglement links particles in ways no classical theory can explain. When one particle falls into a black hole while its partner remains outside, the universe faces a severe tension. How can their shared information remain intact if the pair is separated across an event horizon? This tension inspired the firewall paradox, which suggests the horizon could become a seething wall of high-energy particles that breaks entanglement violently. But this conclusion feels wrong to many physicists. Black holes formed naturally should not suddenly behave like destructive furnaces at their boundaries. Thinking through this paradox feels like watching a fragile thread pulled taut between two worlds. One end lies inside the hole, the other outside. The thread stretches but refuses to snap. Nature rarely breaks its own rules, and so the puzzle pushes us further, urging us to look for deeper connections beneath the surface. Some theorists suggest the solution lies in space-time geometry itself. The fabric of the universe may bend in such a way that what appears separate from one perspective is unified from another. Entanglement might be the glue that holds space-time together, making the inside and outside of a black hole less distinct than they seem. Visualizing this unity evokes the image of two rivers merging beneath the surface. On top, they look separate. Below, they share the same flow. The event horizon might function like that surface, an apparent division that conceals a deeper connection shaped by quantum relationships. Meanwhile, alternative ideas suggest that the interior of a black hole may not collapse to a singularity at all. Quantum effects could create a region of extreme but finite density, a kind of core where space-time stops shrinking. Instead of infinite compression, there may be a bounce, a transformation, or even a bridge to another region of space-time. This possibility leads to the idea of wormholes, tunnels connecting distant points in the universe. Some solutions to Einstein's equations suggest that rotating black holes might contain hidden pathways, although whether these paths are physically stable remains unknown. Wormholes appear naturally in the mathematics, as if the universe is hinting at connections not yet understood. Thinking about wormholes stirs the imagination. It feels like standing at the entrance to a dark forest, sensing that there are paths through the trees, but unable to see where they lead. The possibility is tantalizing, even if the journey remains unreachable. Other researchers consider the idea that the interior of a black hole might link to a future region of our own universe. In this scenario, what falls inside doesn't vanish. It re-emerges, transformed in a distant epoch. Time itself becomes the tunnel, bending into loops and bridges. Reflecting on this reveals how lightly the universe holds our assumptions about causality. We imagine time as a straight line, but physics treats it as malleable clay. Under extreme gravity, time can bend, twist, and merge with space in complex ways. Black holes become sculptors of time as much as sculptors of space. One rarely mentioned truth is that Hawking radiation itself appears thermal, featureless, random, yet must somehow encode the information of everything that fell inside. It's like listening to static on a radio, knowing it secretly contains a symphony. The complexity of that encoding is staggering. Imagining this hidden order evokes the feeling of looking at stars reflected on the surface of a lake. The reflection is blurred, shimmering, distorted, yet the stars behind it remain precise and sharp. Hawking radiation might be the shimmering reflection of information too complex to recognize at first glance. As the black hole evaporates, the horizon shrinks, releasing its stored information bit by bit. In the final moments, the hole becomes tiny, almost delicate, yet its final burst of radiation carries the last encoded traces of everything it consumed. Even in disappearing, it speaks. This evaporation introduces a quiet poetry to black holes. They are not eternal voids, they are temporary states. They form, grow, release energy, store information, and eventually fade. Their lifespan may be longer than the age of the current universe, but they too are part of the cosmic cycle. Recognizing this cycle transforms the emotional tone of black holes. They are not gates to oblivion, they are phases of existence, temporary shapes formed by gravity and time, destined to change, destined to let go. And as we drift through these ideas, another possibility begins to shimmer, one hidden beneath all the others. It hints at a truth deeper than information, deeper than horizons, deeper even than evaporation. Something waiting quietly, like a faint pulse beneath layers of cosmic shadow, inviting us to move deeper into the mystery. Something changes inside the mind when you realize that black holes aren't just strange objects. They are thermodynamic systems, governed by laws as elegant as those that govern heat, pressure, and entropy. This idea, almost never mentioned in school, reveals that black holes have temperatures, entropies, and even pressures. They behave less like cosmic voids and more like engines, storing and redistributing energy with exquisite mathematical precision. Hawking's insight that black holes radiate gave them a temperature, but Jacob Bekenstein's earlier work showed something even more surprising. They have entropy proportional not to their volume, but to the surface area of their horizon. Entropy, often described as disorder, reflects how many microscopic configurations a system can have. For a black hole, this number is unimaginably large, hinting at hidden internal structure. Trying to comprehend this entropy is like imagining a book with trillions of pages, each filled with tiny symbols that shift and rearrange but still encode the same story. The black hole's surface is that book, scribbling and rewriting itself constantly, storing information in ways we can barely describe. Reflecting on this brings a deeper appreciation for how the universe treats information. Nothing is ever truly erased. It may be scrambled, distorted, or hidden behind a horizon, but it persists. Black holes become custodians of cosmic memory, holding on to the details of everything that crosses their boundary. Quantum field theory adds another layer to this picture. Near the event horizon, vacuum fluctuations interact with the intense curvature of space-time, creating the conditions for Hawking radiation. This radiation is faint for large black holes, but grows stronger as the hole shrinks. Ultimately, the black hole evaporates slowly, losing entropy and releasing information in a subtly encoded form. Imagining this evaporation is like watching the slow melting of an ancient glacier. Layer by layer, the ice recedes, revealing sediments trapped for ages. The black hole does something similar, releasing bits of information, one quantum at a time, from its fading surface. There's something lonely and beautiful about that image. A black hole spending trillions of years radiating away its mass, shrinking gradually until the final flicker of its horizon disappears into silence. No explosion, no violence, just a soft farewell encoded in fading particles of light. Yet the universe rarely allows simplicity. As one picture becomes clearer, another mystery opens. Some researchers propose that black holes store information in soft hair, subtle quantum excitations on their surfaces. Others suggest that information is preserved in correlations within Hawking radiation. Still others imagine a deeper layer of space-time where information flows through hidden channels. Visualizing these possibilities evokes the image of intricate embroidery sewn onto a dark fabric. From a distance, the cloth seems plain, but up close, delicate threads reveal patterns woven with intention. Black holes appear silent and featureless, yet their horizons may contain an astonishing richness beneath the apparent darkness. Entanglement is central to this richness. When particles are entangled, their states are linked regardless of distance. Black holes require vast webs of entanglement to maintain the smoothness of space-time near their horizons. Without this structure, the horizon could become violent or unstable, something nature seems unwilling to allow. Thinking about entanglement in this context suggests that space-time itself may be woven from relationships rather than objects. The horizon becomes a quilt of connections, with each thread representing quantum correlations that bind the interior and exterior worlds in subtle ways. This leads to the idea that space-time geometry is emergent, a large-scale consequence of countless microscopic interactions. If so, the event horizon is not a place but a phenomenon, arising from the collective behavior of deeper degrees of freedom. Black holes become gateways not to destruction, but to fundamental truths about the nature of reality. Visualizing this emergence feels like watching frost form across a window pane. At first, the glass is clear, then delicate crystals branch outward, creating intricate patterns. The frost emerges from molecules interacting, not from any single cause. Space-time may arise the same way, patterns emerging from unseen ingredients. Another overlooked chapter involves the idea of complementarity. This principle suggests that no single observer can access all aspects of a black hole. What is destroyed from one perspective is preserved from another. Both descriptions are valid, even if they appear contradictory. The universe maintains consistency through viewpoint-dependent truths. This idea reshapes our understanding of paradox. It declares that contradiction is sometimes a matter of perspective, not failure. Black holes, instead of breaking the rules, expand them, offering multiple consistent views that cannot be observed simultaneously. Researchers exploring quantum gravity propose even stranger possibilities. Loop quantum gravity suggests that space-time inside a black hole might bounce, transforming collapse into expansion. String theory imagines black holes as brains, vibrating surfaces with holographic descriptions. Some models propose fuzzballs, where the interior is replaced entirely by tangled structures of strings. Contemplating these worlds is like peering into a dream within a dream. Layers unfold, boundaries fade, and familiar concepts dissolve into something richer. It becomes clear that black holes are not the end of physics. They are the doorway to its next chapter. Meanwhile, the connection between black holes and entropy hints at something cosmic in scale. The universe itself has entropy, increasing over time. Stars burn, galaxies evolve, and energy spreads outward. Black holes store vast amounts of entropy, acting as reservoirs that absorb and redistribute the universe's disorder. This role gives them an unexpected significance. They are not mere curiosities. They are central to thermodynamic balance on vast scales. Even the universe's future may depend on how black holes form, merge, and evaporate. Imagining this cosmic role invokes a feeling of reverence. Black holes become quiet custodians of the universe, absorbing chaos and contributing to the grand flow of energy and information. Their darkness is not emptiness. It is a function, a purpose, a quiet stewardship written into the laws of thermodynamics. And somewhere within all these ideas, entropy, evaporation, holography, entanglement, there lies a clue to something older, a truth not yet fully understood, but felt in the spaces between theories. It glimmers faintly, like a hidden star seen only from the corner of your eye, waiting for us to drift closer as the journey continues. Far into the future, long after every familiar star has vanished, black holes will dominate the universe, not because they seek power, but because they endure. Stars exhaust their fuel, galaxies drift apart, and matter becomes thin and cold. Yet black holes persist, holding on to mass and memory as the cosmos around them fades into silence. This longevity gives them a unique role in the story of everything. Cosmologists studying the far future describe a universe entering what is called the degenerate era, when only the remnants of stellar evolution remain. White dwarfs, neutron stars, and black holes linger in the darkness, slowly interacting through gravity. Over trillions of years, even these remnants collide, merge or drift apart, leaving black holes as the dominant structures. Imagining that cosmic loneliness feels like standing in an enormous desert at night, the sky empty of starlight, the air still. Yet within that stillness, the black holes remain, quiet, massive, patient. Their gravity continues shaping whatever stray particles wander close enough, long after the vibrant days of star formation are forgotten. This vision carries a weight that's difficult to express. We grow up surrounded by light, sunlight, lamps, screens, stars. Our understanding of the universe is soaked in brightness, but the future belongs to the dark, and in that darkness, black holes become the last storytellers of cosmic history. Hawking radiation slowly erodes them over unimaginable stretches of time. A black hole the mass of a star would take around 1067 years to evaporate. Supermassive black holes last even longer, up to 10 to 100 years. Numbers so large, they feel like poetry rather than quantities. In that time span, every element of existence changes, except their steady presence. Trying to feel the scale of those timescales is like trying to sense the movement of continents beneath your feet. The motion exists, but it's too slow for human perception. The universe's story unfolds on scales our lifetimes can barely register, and black holes are its longest chapters. Eventually, though, even they begin to fade. Hawking radiation strengthens as black holes shrink. What was once cold, dim emission becomes brighter and hotter until the black hole reaches its final stages. The last moments are rapid, a burst of energy, a final sigh of stored information, and then the horizon dissolves into nothing. This evaporation paints a strangely poetic ending. The darkest objects in the universe die by releasing light, returning their contents to the cosmos piece by piece. They do not collapse further, nor do they erupt violently. They simply release their history, encoded in radiation, back into the universe. The idea that everything a black hole consumed eventually returns feels unexpectedly hopeful. Nothing is held forever, nothing is lost. The universe retrieves its secrets in the end, patiently collecting each bit of information as the ages pass. After the black holes evaporate, the universe enters its darkest phase. Cold and empty, nearly motionless, particles become incredibly rare. Expansion pushes everything farther apart. Temperature asymptotically approaches absolute zero. This era, sometimes called heat death, represents the end of usable energy and the fading of all structure. Contemplating this distant future evokes a quiet sadness. We are accustomed to a universe filled with vibrant galaxies, colorful nebulae, and warm stars. But in the farthest reaches of time, only silence remains. The cosmos becomes a vast, dark ocean where nothing stirs. Yet even in this desolate epoch, physics continues. Virtual particles still flicker briefly into existence. Space-time still curves subtly. Quantum fields still hum with the faintest possible energy. The universe, though cold, is not dead, it simply rests. That rest is strangely comforting. It reminds us that existence doesn't require constant motion, brightness, or sound. Sometimes, the universe chooses stillness, and black holes, having shaped the cosmos through countless epochs, are part of the story that leads to that final calm. Some cosmologists speculate about new beginnings beyond this calm. Perhaps quantum fluctuations could spark fresh expansions. Perhaps black hole evaporation seeds new universes. Perhaps the story never truly ends. It only transforms. These ideas remain speculative, but they reveal how deeply black holes intertwine with our theories of origins and endings. Thinking about these possibilities brings a gentle awe. Black holes don't just shape galaxies, they help shape our understanding of existence itself. They teach us about entropy, time, information, and the far future. Their darkness conceals lessons about endurance and transformation that shine brighter than any star. And as we drift through these immense cosmic eras, it becomes clear that the universe is not telling a story of loss. It is telling a story of cycles, stars forming, collapsing, feeding black holes, which one day release their contents back to the void. Birth, transformation, release, over and over. Inside that cycle lies a quiet truth. Everything changes form, but nothing disappears. What seemed like an ending becomes part of another beginning. The universe writes and rewrites itself endlessly, using black holes as punctuation marks, pauses in the cosmic sentence where gravity gathers its thoughts. Somewhere within this rhythm, a deeper understanding begins to take shape. It whispers that even the darkest moments contain hidden transitions, waiting for the right conditions to unfold. And just beyond that whisper, the mystery deepens, guiding us gently toward what lies in the shadows ahead. Something quiet happens inside you when you confront the idea that parts of the universe will forever remain unknowable. Black holes embody that boundary better than anything else. They stand as reminders that reality has limits, not because the universe is incomplete, but because our perspective is. No matter how advanced our technology becomes, the interior of a black hole remains hidden behind a one-way curtain. That boundary reflects our own limitations back at us. Physicists have sent incredible machines into space, built detectors deep underground, and developed equations that can describe space-time with astonishing accuracy. Yet the horizon still says, "You cannot see beyond this." That refusal isn't rooted in hostility. It's simply the nature of the geometry. The edge of a black hole isn't a wall, it's a shift in what the universe allows us to witness. Imagining that constraint feels like walking through a fog so thick that even your extended hand fades from view. The world doesn't end where the fog begins. Your vision does. Black holes carry the same truth. Their interior continues, but our access does not. That quiet separation produces a kind of cosmic humility, gently reminding us how small we are. Reflecting on that humility can be strangely soothing. Life often demands answers, certainty, clarity, understanding, but the universe suggests that mystery is not a flaw, it is part of the fabric of existence. Black holes are invitations to accept that some questions will always linger just beyond reach, glowing faintly at the edge of comprehension. Another layer of introspection appears when you consider how small human timescales are compared to cosmic ones. The lifespan of a black hole dwarfs the lifespan of stars, civilizations, species, and even entire branches of the cosmic web. They endure across epochs we cannot meaningfully imagine. Their existence stretches far beyond the boundaries of human memory. Trying to place yourself within that timescale evokes a quiet ache. You realize that our entire history, from our first breath to our final thought, is a flicker compared to the life of a black hole. Yet this does not diminish us. It highlights the preciousness of our fleeting moments, the rarity of consciousness within this vast or indifferent universe. Visualizing the contrast is like watching a tiny candle glow beneath the night sky. The flame is fragile, small, easily extinguished. The sky is endless, cold, ancient. And yet for a moment, the candle creates warmth and meaning in a place where none is required. conscious beings do something similar within the cosmic landscape. Black holes also raise unsettling questions about identity. If information is never destroyed, what does that say about the patterns that make us who we are? If the universe preserves every quantum detail, then the distinction between existence and non-existence becomes blurry. We become not isolated beings, but temporary arrangements of information carried along by cosmic flows. Thinking about yourself as a pattern rather than a permanent object can feel disorienting. It challenges the sense of solidity you rely on. But it also reveals a comforting truth. The universe is full of transitions, stars becoming gas, gas becoming planets, planets becoming dust, dust becoming stars again. Patterns shift, but the ingredients persist. This persistence mirrors what black holes show us about information. When something falls into a black hole, its arrangement changes, but its essence is encoded on the horizon. The universe seems to insist, softly but firmly, that nothing truly vanishes. Everything contributes to a larger tapestry that outlives all individual forms. Considering this, you might feel a trace of melancholy. Humans tend to cling to permanence, even as everything around us flows and reshapes. Black holes force us to acknowledge that change is the norm, and permanence is the illusion. But this realization doesn't have to be sad. It can be freeing, offering a perspective that relieves the pressure to cling so tightly to what cannot be held. A similar emotional shift occurs when you ponder how black holes warp time. Their intense gravity slows clocks dramatically. To someone far away, a traveler falling in appears to freeze, but from the traveler's viewpoint, their journey continues without interruption. This duality suggests that time is not absolute, and neither is perspective. The idea that time depends on where you are and how you move is unsettling at first. Then it becomes comforting. It means that reality is more flexible than the rigid tick of a clock suggests. It means that our personal experience, our proper time, is as valid as any external measurement. Each of us carries a private timeline shaped by our journey. Thinking in these terms makes the universe feel more intimate. If time and space flow differently for everyone, then we are all traveling unique paths through a landscape shaped by mass, motion, and gravity. Black holes dramatize these differences, but they exist everywhere, even in the gentle curvature around Earth. Another overlooked emotional truth is how black holes challenge the human desire for control. We spend much of our lives trying to predict, manage, and manipulate our circumstances. But black holes represent regions where prediction fails, where equations grow incomplete, and where certainty dissolves. Their presence teaches us to let go, just a little. Letting go doesn't mean surrendering to chaos. It means accepting that some forces are larger than us. It means allowing space for wonder, acknowledging the limits of knowledge, and embracing the quiet beauty of the unknown. Black holes embody that lesson silently. This shift in perspective can feel like stepping into a quiet cathedral. The immensity humbles you, but the silence welcomes you. The unknown is not hostile, it is simply vast. And within that vastness, you find room to breathe, to think, to reflect on your place in the story. Another facet of this introspection comes from the role black holes play in endings. They mark the final stage in the life of massive stars. They represent collapse, compression, and the limits of structure. In a human context, we avoid thinking about endings, but the universe doesn't avoid them. It integrates them into its rhythm. Understanding that rhythm softens the fear of finality. Black holes show that endings are transitions, not voids. They transform what came before into something new, something encoded, something enduring. Their presence suggests that even the darkest moments hold seeds of transformation. As we drift deeper into this existential territory, the emotional landscape begins to change. The awe remains, but it's tinged with something more reflective, an awareness of fragility and resilience. The cosmos feels larger, stranger, quieter, and somewhere within that quiet, something faint begins to take shape, as if the universe is preparing to reveal a truth hidden beneath layers of gravity and silence. There's a quiet strangeness in realizing that black holes expose the limits of objectivity. We like to believe the universe is the same for everyone, everywhere, all the time. But near a black hole, two observers can disagree not just about what happened, but about whether something happened at all. Reality becomes a negotiation between perspectives. That idea, unsettling as it sounds, reflects the fragility of the frameworks we take for granted. Einstein's relativity tells us that space and time are flexible, shaped by motion and gravity. Near a black hole, this flexibility becomes radical. Two observers watching the same event witness different histories. One sees a smooth fall inward, the other sees a slow freeze at the horizon. Both descriptions are correct within their own frames. Thinking about this duality feels like listening to two versions of the same story, one told in whispers, the other in echoes. The meanings overlap, but never fully align. Black holes offer a reminder that our experiences, too, are shaped by where we stand, what we carry, and how we move through the world. This emotional truth can be unsettling. Humans crave consistency. We anchor ourselves in shared meanings and shared moments. Yet the universe seems to suggest that multiplicity is natural, that different truths can coexist without one invalidating the other. Reality is less a solid wall and more a shifting landscape shaped by viewpoint. Another layer of existential weight emerges when you consider how small the human story is compared to cosmic scales. Individual lives feel significant to those living them, yet on the scale of galaxies, civilizations rise and fall unnoticed. The universe unfolds whether or not we witness it, and black holes exemplify that impartiality. Imagining this cosmic indifference can feel disheartening at first. The idea that the universe carries on without us seems cold, but then a softer interpretation emerges. Because if the universe is not concerned with us, it also places no burden on us. We are free to create meaning rather than search for it in the stars. This freedom carries a kind of serene melancholy. You realize that meaning exists because we create it, through memory, emotion, curiosity. Even in a universe filled with unimaginable distances and silent horizons, consciousness becomes a lantern illuminating a tiny part of the darkness. Black holes also challenge our idea of place. When space-time curves intensely, the distinction between here and there dissolves. Directions lose meaning. Inside the horizon, all paths lead inward. That dissolution resonates with the human experience of losing a sense of direction emotionally or personally. Gravity becomes a metaphor for life's inescapable pulls. Reflecting on that resemblance reveals a deeper human truth. Everyone experiences moments where the path forward narrows, where choices reduce, where the future feels like a funnel. In those moments, black holes remind us that movement remains possible, even when the landscape shifts in ways we cannot control. One of the most haunting aspects of black holes is how they distort light. Photons skimming close to the horizon can loop around the hole, orbiting multiple times before escaping. To a distant observer, this creates a thin, luminous ring, the last light of the universe's most stubborn photons. These orbits, called photon spheres, represent a delicate balance between capture and escape. Trying to imagine that light circling endlessly evokes a sense of longing. The photons are neither free nor consumed, caught in a graceful, eternal loop, their fate balanced on the edge of darkness. That fragility reflects the delicate nature of many human decisions. the ones where a single step determines everything. The image of that ring, captured for the first time by the Event Horizon telescope, feels strangely emotional. It's not just a photograph, it's a boundary between knowable and unknowable, a thin ribbon of light marking the edge of understanding. Seeing it is like glimpsing the outline of a secret the universe has carried since the beginning. Another dimension of existential reflection emerges from the idea that black holes may encode the story of everything they consumed. If information remains in some scrambled form, then the universe is filled with preserved histories, hidden within gravitational boundaries. Our own memories fade, but cosmic memory persists. This contrast nudges an intimate question into view. What does it mean that the universe remembers more than we do? Humans forget moments, names, faces, entire years, yet black holes preserve quantum details of every particle they swallow. The cosmos keeps a record we cannot access, a ledger written in gravity. Thinking about this evokes a gentle ache, like reading an unfinished letter. The universe holds far more than we can retrieve, and that asymmetry is both tragic and beautiful. It means there is meaning everywhere, even if we cannot see it directly. It means nothing is ever truly erased. Black holes also reveal how fragile boundaries are. Outside the horizon, space behaves one way, inside, another. But the boundary itself is not a wall, it is a condition, a place where the rules shift. Humans experience similar boundaries in emotional terms. A single event can redraw the landscape of a life, creating a before and after. This recognition softens the fear of change. If even space-time has thresholds where the rules transform, perhaps personal transitions are not failures, but natural shifts in the geometry of our lives. Black holes become metaphors for the inevitability of change, the fluidity of identity, the constant rewriting of internal structure. Another quietly profound idea comes from the way black holes link quantum mechanics and general relativity, two theories that normally refuse to cooperate. The horizon is where these frameworks meet awkwardly, struggling to describe the same phenomenon. Their tension mirrors the human struggle between emotion and logic. Life rarely fits perfectly into one model. We interpret moments through both feeling and reason, and sometimes these perspectives clash. Black holes remind us that contradictions can coexist without invalidating each other. Complexity is natural, not a failure of understanding. As the emotional arc deepens, a broader question begins to arise. If black holes show us the limits of observation, the persistence of information, the relativity of time, and the fragility of perspective, what are they ultimately teaching us about existence? Are they warnings, mirrors, invitations, errors? And just as the mind begins to approach that overwhelming question, something shifts, quietly, subtly, like a faint hum beneath the silence. It feels as though the universe is preparing to reveal one last secret, hidden not in the mathematics, but in the meaning behind the mystery itself. There's a quiet moment after learning everything we can about black holes, when the scientific mystery becomes something more personal. You begin to sense that the true enigma isn't the gravity or the geometry. It's what these impossible objects imply about the universe itself. They highlight how much reality hides beneath the surface, how much lies beyond our reach, and how our understanding is always provisional, always evolving. Every discovery about black holes arrives with a shadow, a reminder of what remains unknown. Hawking radiation explained part of their behavior, but raised new paradoxes. Holography resolved some contradictions, yet opened others. Each step forward reveals a deeper layer, like peeling back the petals of a flower made of equations and silence. Thinking about these layers evokes a sense of softness. The universe is not withholding answers to frustrate us. It simply contains more depth than any finite mind can hold at once. Black holes embody that depth, each one a knot in the cosmic fabric where meaning concentrates and stretches until our models begin to blur. This blurring is not a failure of science. It's evidence that reality is richer than our frameworks. Humans create theories to organize the world, but the universe is under no obligation to fit neatly into them. Black holes stand as monuments to this mismatch, elegant reminders that truth is not limited to what we can describe. One often overlooked aspect is how black holes connect to the quantum vacuum, a sea of energy and fluctuations that fills all of space. Close to the horizon, these fluctuations become amplified, revealing structure in what we once called emptiness. The closer we look, the less empty the vacuum appears. Even darkness, it seems, contains its own form of presence. Visualizing these fluctuations feels like watching dust illuminated by a narrow beam of sunlight. In the dimness, the air looked empty, but under the light, countless tiny motes sparkle and drift. Black holes expose the universe in the same way, revealing patterns hidden in regions we once assumed were featureless. This shift in perception carries an emotional weight. Much of life is spent overlooking the subtleties around us, missing the intricate details that shape our days. Black holes remind us that the unseen world can be full of structure, meaning, and quiet motion, even when it looks dark from afar. Another fascinating idea involves the possibility that the universe itself may behave like a black hole on the largest scales. Some cosmologists propose that cosmic expansion and horizon-like boundaries mirror the behavior of event horizons, suggesting deep symmetries between the largest and smallest structures. If true, the universe and black holes may be reflections of each other across different scales. Imagining this symmetry feels like seeing your own reflection in a lake and realizing the lake reflects the sky as well. Everything mirrors everything else, and boundaries blur. The cosmos becomes less a collection of isolated phenomena and more a single, interconnected structure. This interconnectedness leads to another profound consideration. The universe might be shaped more by relationships than by objects. Entanglement, curvature, information flow, these are not standalone properties. They depend on connections, interactions, shared states. Black holes magnify these relationships until they dominate the physics. Reflecting on that dependence nudges a quiet truth into awareness. Nothing exists alone. Stars form in clusters, galaxies evolve in groups. Black holes grow through mergers. Even the vacuum depends on fields interacting. It's a universe built from bonds, not isolation. Black holes also raise the question of whether space and time are fundamental at all. Some physicists argue that space-time emerges from deeper layers of quantum information. If so, the event horizon is not a physical location, it's a transition between states of information. The geometry is secondary, the information is primary. Thinking this way reshapes everything. Instead of asking what the interior of a black hole looks like, we begin asking what the interior means, what patterns define it. What rules govern the flow of information there? The questions shift from spatial to conceptual, revealing new ways to interpret the cosmos. This conceptual shift mirrors changes in human understanding. As we grow, we often realize that the most important answers aren't about where things are, but what they signify, how they influence us, how they connect, how they transform. Black holes echo this lesson, showing that depth is not purely spatial. Another surprising idea arises from quantum gravity research. The interior of a black hole might grow over time, even after the event horizon stops expanding. This interior growth suggests that something inside the black hole continues unfolding, as if its hidden space keeps blooming in darkness. From the outside, the black hole appears unchanged. Inside, its volume increases. This hidden growth is strangely poetic. It suggests that even in the deepest isolation, something continues expanding. something grows in the dark, something unseen finds room to become larger. It's a cosmic metaphor for inner transformation, the kind that occurs quietly beyond the notice of the outside world. From a physical standpoint, this growth arises because space-time curvature stretches interior regions more quickly than the horizon contracts. It's a counterintuitive idea. The inside can grow while the outside shrinks, yet the mathematics supports it, revealing that black holes may contain vast interior landscapes, far larger than their external size suggests. Imagining those hidden landscapes evokes an odd kind of longing. What exists in those volume-rich regions? What paths might space-time take inside them? The interior becomes a realm of potential rather than emptiness, a place where the universe creates room for possibilities we cannot visualize. Some theorists go further, proposing that consciousness itself might influence how we perceive horizons. Not because consciousness alters physics, but because horizons depend on the observer. Different observers perceive different boundaries. This means the universe draws its lines in ways that depend on awareness. Reflecting on this idea encourages a deeper sense of presence. It reminds us that our experience of reality is shaped by our position, our motion, our perspective. We are part of the fabric, not separate from it. Black holes highlight that entanglement between observer and observed. The emotional crescendo arrives when all these realizations converge. Black holes are not just astrophysical phenomena. They are mirrors showing us the limits of knowledge, the flexibility of time, the persistence of information, and the beauty of the unknown. They force us to accept that some truths lie beyond grasp, yet still deserve contemplation. And just when it feels like the mystery has reached its peak, something softer appears beneath the complexity, a sense that the universe, despite its enormity, holds space for us, for our questions, our fleeting lives, our small flickers of awareness. The darkness does not erase us, it contextualizes us. Somewhere in that understanding, a quiet peace emerges. A feeling that the universe is vast enough to include our confusion, our curiosity, our longing for meaning. And just beyond that peace, a final revelation waits, one that gathers all the threads together, ready to settle into stillness as we drift toward the closing moments of this journey. As the journey through black holes draws to a gentle close, a softer understanding settles in. The mysteries we explored, gravity's strange geometry, time's uneven flow, horizons that separate yet connect, begin to feel less like puzzles and more like quiet invitations. These cosmic enigmas no longer press for answers. They drift around you like slow-moving currents of thought, reminding you that curiosity itself is a form of connection with the universe. Somewhere in the stillness, you might sense echoes of the first question that opened this night. The darkness of black holes, once intimidating, now feels calmer, more familiar. Not because you can see inside them, but because you've learned to sit comfortably with the unknown. A peaceful acceptance grows, the kind that comes from realizing that uncertainty is natural, spacious, and even beautiful. Throughout the journey, science revealed truths about light, entropy, information, and the shape of space-time. But beneath those discoveries flowed something quieter, a reminder of how small we are, and yet how astonishing it is that we get to witness any of this at all. Black holes do not diminish the human experience, they expand it, giving context to our fleeting existence and showing how rare consciousness truly is. Letting these thoughts settle feels like allowing dust to drift down in a sunbeam. No urgency, no demand, just gentle motion. The universe becomes less a collection of unreachable secrets and more a vast, calm ocean through which we slowly travel. Every question becomes a ripple, every insight a soft glow beneath the surface. And even though black holes will forever guard parts of their interior, their presence tells a story that doesn't require full understanding. They teach through contrast, light and darkness, knowledge and mystery, permanence and change. They show that some truths arrive not through answers, but through reflection, through the willingness to pause and listen to the quiet rhythm of existence. If this long drift through science and wonder brought you even a moment of peace, I'm sincerely grateful you shared your time here tonight. And if you'd like to help this calm corner of the universe reach others who might need a gentle escape, you're warmly invited to leave a like and subscribe. Small gestures like that create ripples far beyond the screen. Before we part ways, there's one last thought worth holding. Every horizon, cosmic or personal, marks a boundary that feels final until you cross it. On the other side, new meaning takes shape. Change is woven into the structure of the universe. Even the darkest objects evolve, release their secrets, and fade into new forms. Nothing stays still forever, and that impermanence is part of what makes existence precious. So if tonight left you with more questions than answers, that's perfectly fine. The universe itself is full of unanswered questions, and you're moving through it exactly as you should. Curious, uncertain, human. The fact that you seek understanding at all places you in rare company among the stars. Wherever you are, whatever time it is, I hope you feel a little more grounded, a little more connected to the quiet fabric of the cosmos. The distance between you and the farthest galaxy shrinks when you allow yourself to imagine it. The borders between inner and outer space blur. Everything becomes part of the same gentle flow. And as the night settles fully, let this final moment rest softly around you. The universe may be vast, but your presence within it adds something unique, something felt, even if faintly, like a single warm light flickering in the silence. Thank you for drifting through these shadows and stars. May your dreams tonight be as deep and gentle as the dark between galaxies.